last week my group 2 presented, and I'm presenting the refrigeration cycle for my group. And we covered the refrigeration cycle. So here's the main purpose of this lab. So first we need to determine the inlet power, and we determine the heat that was produced from this cycle, and then the coefficient of performance by this. And then we need to compare the ideal versus the real cycle on a pressure entropy diagram. So a little bit of theory on how a refrigeration cycle works. So there's 4 main stages to refrigeration cycles. And that's the compression stage, condensation, expansion, and evaporation. And then the way we choose a refrigerant is that it needs to have a low boiling point so it can switch between gas and a liquid easily. And the main reason why this works is that it has an expansion valve that when the fluid goes through, it causes the fluid to cool. And then when it compresses, it causes the heat up. And then we use that force to drive refrigeration. So a little bit more theory on the next slide. Right here we see a pressure entropy diagram. And then you see the 4 stages that we have. So we have start with compression, condensation, and the expansion, and then the evaporator. As you see here, the expansion is marked with the TXV, and this is the valve that was mainly used in refrigeration. And so we also have the PV diagram and the entropy diagram, temperature entropy diagram here. And this is a schematic of the refrigeration cycle. So this is for an ideal system. If it were a real system, it would be, the entropy would increase after each compression and expansion. And this is our setup. So this is the computer-controlled vapor compression refrigeration unit that we use. Very easy to use, and we just flip a few buttons and it runs, and then we get all of our readings from the computer. So as you can see, it's equipped with a compressor, evaporator, and then a condensator. So here's a procedure that we follow on this experiment. So first we start up the software, and then we set the compressor to 40% of the power, and then we vary the flow rates and measure and took the temperatures at different positions and the pressures at different positions. And the flow rates that we use were listed here. We start off with 5 and 3, as you see. And we analyze the data, and then we can compare it. Here's some of the raw data we have. And then there's a little bit of calculations that we did. So as you can see, there's 2 ways of finding the coefficient of performance. So one is by calculating the heat using the constant CP. And then here we have the flow rate of 5 liters per minute converted into kilograms per second. And we use that to find the heat. And then we multiply it out, and then we're given the work. And so we divide by the total work, and then we have a coefficient of performance of 4.932. This one, you're supposed to find the enthalpies at different locations. So in conclusion, the coefficient of performance is proportional to the flow rate. Any questions?
I guess just ending with that note of the coefficient of performance being proportional to flow rate, right? What would be an issue with, I guess, running your flow rate at infinity? I guess like what could be, there has to be some drawback, or is there, I guess?
It's just impossible to reach a certain flow rate. And then you need to have some kind of pump in order to get it to that. So I think it's not achievable.
Yeah, the piping and everything, yeah.
Why is this slide not complete?
It's just didn't do it.
Alright, I'll go to it. That's all. The list should be complete as